What if everything we think we know about the cosmos is wrong? Picture this: every star, every galaxy, every swirling nebula we see through our telescopes might be just a tiny fraction of the story. There are mysteries out there so profound, so baffling, that even our sharpest scientific minds are still searching for answers. And that's exactly what makes the universe endlessly fascinating. It's not just a void of darkness, it's a playground of puzzles waiting to be solved, a cosmic riddle written in starlight and shadow. Today, we're diving deep into 30 of the most mind-bending theories scientists have put forward to explain space's biggest mysteries. From the invisible grip of dark matter holding galaxies together to the eerie silence behind the Fermi paradox, why, in such a vast and ancient universe, haven't we found any signs of other intelligent life? These aren't just abstract ideas reserved for textbooks. They're thrilling glimpses into how we might one day understand the true nature of reality itself. Each theory is a piece of a grand cosmic puzzle, and together they form a tapestry of human curiosity, imagination, and our relentless drive to uncover the secrets of the cosmos. This journey is for everyone, whether you're an avid stargazer or someone who simply looks up at the night sky and wonders. We'll break down complex concepts into relatable ideas using clear analogies and a touch of playful curiosity. So get comfortable, open your mind, and let's explore the edges of what we know and what we're still striving to understand. By the end, you might not have all the answers, but you'll walk away with a deeper sense of awe for the universe and our place within it. Let's begin. Our first stop on this journey takes us to one of the most expansive and mind-bending ideas in all of cosmology, the multiverse theory. At its heart, this concept proposes that our universe, with all its hundreds of billions of galaxies, might not be alone. Instead, it could be just one single bubble in a vast, frothing cosmic ocean, one universe among a potentially infinite number of others, each with its own unique set of physical laws and constants. This isn't just wild speculation. The theory finds its roots in two of the most robust pillars of modern physics: quantum mechanics and cosmic inflation theory. Quantum mechanics introduces the idea of probability and superposition at the most fundamental level, while inflation theory describes how the universe expanded exponentially in the first fraction of a second after the Big Bang. Many physicists suggest that this inflationary period didn't just happen once, but is an eternal process, constantly giving birth to new universe bubbles in an ever-growing multiverse. This leads us to one of the most compelling arguments for the multiverse, the fine-tuning problem. The fundamental constants of our universe, like the strength of gravity, the mass of an electron, or the force that holds atomic nuclei together, seem perfectly calibrated to allow for the existence of stars, planets, and life. If any of these values were even slightly different, matter as we know it wouldn't coalesce, chemistry would be impossible, and the universe would be a barren, lifeless void. The odds of this perfect balance happening by chance are astronomically small, almost like winning the lottery an infinite number of times in a row. The multiverse offers an elegant solution to this puzzle. If there are an infinite number of universes, each with randomly determined physical laws, then it's no longer a miracle that we find ourselves in one that is habitable. In an infinite cosmic landscape, every possible configuration of reality exists somewhere. We simply occupy the one that allowed us to be here to observe it. To visualize this, picture a boundless sea of soap bubbles, each bubble representing an entire universe, completely self-contained and possibly governed by entirely different rules. In one bubble universe, gravity might be so strong that it crushes all matter into black holes instantly. In another, the forces might be too weak to ever form atoms. Some universes might flicker in and out of existence in a nanosecond, while others could be utterly silent and dark, never giving rise to complexity. Our universe is just one bubble where all the dials happen to be set exactly right. This concept transforms our perspective from a single, special universe to one of countless possibilities, dramatically redefining our place in the grand scheme of existence and challenging the very notion of what is meant by everything. Moving from the almost philosophical vastness of the multiverse, we now turn our attention to a mystery that is far more immediate and tangible, one that literally holds our universe together. We've known for decades that the cosmos contains far more than what meets the eye, or our most powerful telescopes. In fact, the stars and galaxies we see are just the visible glitter on the surface of a much deeper, darker ocean. This brings us to one of the most significant and persistent puzzles in all of science: dark matter. Scientists estimate that this invisible substance makes up about 27% of the entire universe, outnumbering the ordinary matter that makes up our planets, stars, and ourselves by a ratio of about 5:1. We cannot see it because it does not emit, absorb, or reflect any light. It is completely transparent to the entire electromagnetic spectrum. So how do we even know it's there? The evidence comes from its gravitational footprint. We can observe its ghostly pull on the things we can see. For instance, when we look at how galaxies spin, the stars on the outer edges are moving so fast that they should be flung off into the void, much like water flying off a spinning wet tire. The fact that these galaxies don't tear themselves apart points to the presence of a huge amount of invisible mass, a gravitational glue holding them together. This missing mass is dark matter. The leading candidate for what this mysterious substance could be is a hypothetical particle known as a WIMP, which stands for Weakly Interacting Massive Particle. The name itself is a perfect description of its proposed properties. Massive means it has substantial weight, contributing to its strong gravitational influence. Weakly interacting means it ignores both the electromagnetic force and the strong nuclear force, allowing it to pass through ordinary matter almost as if it weren't even there. Trillions of these particles could be streaming through your body every second without you ever feeling a thing. Their only way of making their presence known, aside from gravity, would be through the weak nuclear force, the same force responsible for radioactive decay. The hunt for these elusive particles is one of the most intense and fascinating efforts in modern physics. Because WIMP would interact so rarely and feebly with normal matter, detecting them requires incredibly sensitive equipment shielded from all the cosmic noise and radiation that constantly bombards the Earth's surface. This is why scientists have built ultra-sensitive detectors deep underground, in abandoned mines and tunnels beneath mountains. These massive layers of rock act as a natural shield, blocking out most interfering particles. At the heart of these labs, vats of ultra-pure liquefied xenon or germanium are kept at extreme temperatures, waiting for the once-in-a-lifetime event where a WIMP might bump into the nucleus of one of these atoms. The resulting tiny flash of light or minute electrical signal would be a discovery of monumental proportions, a direct glimpse into the 85% of the universe that has until now been completely hidden from us. This theory isn't just about finding a new particle, it's about completing our fundamental picture of the cosmos. The gravitational effects of WIMP provide the scaffolding upon which the entire universe is built. In the early universe, slight density fluctuations in the dark matter web acted as gravitational seeds, pulling in ordinary gas that eventually ignited into the first stars and coalesced into the galaxies we see today. Without dark matter, the universe would be a much smoother, darker, and emptier place. The ongoing search for WIMP is a testament to our determination to understand the full story of the cosmos, to move from simply observing its gravitational shadow to finally identifying the substance that constitutes the vast majority of everything. But what if we're looking at this puzzle from the wrong angle entirely? Instead of searching for an invisible substance that makes up the vast majority of the universe, an alternative theory proposes a far more radical idea. perhaps our fundamental understanding of gravity itself is incomplete. This is the core premise of MOND, or modified Newtonian dynamics, first proposed by physicist Mordechai Milgrom in the early 1980s. MOND suggests that gravity doesn't behave exactly as Newton or Einstein described, especially in environments where its pull is incredibly weak, like the outer edges of galaxies. In these regions of extremely low acceleration, Milgrom theorized, gravity gains a tiny bit of extra strength, a subtle modification to the known laws of physics. This extra gravitational kick would be just enough to hold a fast-spinning galaxy together without requiring any additional, invisible matter. The most compelling evidence for MOND comes from the very data that revealed the dark matter problem in the first place: galaxy rotation curves. For many spiral galaxies, the predictions made by MOND align almost perfectly with the observed speeds of stars orbiting far from the galactic center. In these cases, the observed motion of visible matter is all you need to explain the galaxy's structure. No dark matter halo is required. For its proponents, this elegance is a major point in MOND's favor. It offers a direct solution using the matter we can see, sidestepping the decades-long and so far unsuccessful hunt for hypothetical dark matter particles. It argues that the mystery isn't a missing ingredient in the universe, but a missing clause in our physical laws. However, the story is far from settled. While MOND excels at explaining the behavior of individual galaxies, it faces significant challenges when applied to the largest scales in the cosmos. The theory struggles to account for the observed gravitational effects within massive galaxy clusters. When galaxies collide, the visible matter and the gravitational center of mass can become separated, and observations of these events, such as the famous bullet cluster, show a gravitational field that doesn't align with the visible gas and stars. This is precisely what the dark matter model predicts: a cloud of invisible WIMP passing through the collision while the visible matter slows down. But it creates a major hurdle for MOND, which ties gravity directly to the visible mass. Furthermore, MOND, in its original form, does not seamlessly integrate with Einstein's theory of general relativity, our best description of gravity on a cosmic scale, making it difficult to explain phenomena like the bending of light around massive objects or the evolution of the entire universe. This fundamental tension is why the majority of the physics community continues to favor the dark matter hypothesis. The consensus view is that while MOND is a creative and intriguing idea, the preponderance of evidence from multiple independent lines of inquiry, from galaxy rotations to the cosmic microwave background to the large-scale structure of the universe, all point toward the existence of a yet-to-be-detected particle. The search for dark matter is a bet on the completeness of our foundational theories, suggesting that we simply need to find the missing piece of the particle puzzle. MOND, on the other hand, is a bet on a scientific revolution, a need to fundamentally rewrite one of our most fundamental understandings of the physical world. Both paths lead to a profound transformation of physics. One requires discovering a new part of the universe, while the other demands redefining the very rules that the universe plays by. Now, if you thought the debate between dark matter and modified gravity was a paradigm shift, prepare to have your entire perception of reality turned inside out. We're venturing into the realm of one of the most profound and counterintuitive ideas in theoretical physics, the holographic principle. This theory proposes a staggering possibility that our seemingly rich, three-dimensional universe with all its depth and volume might actually be a projection. A cosmic illusion. The reality we experience could be nothing more than a hologram encoded on a distant, two-dimensional surface that surrounds us, like the information on the surface of a giant spherical DVD. The seeds of this radical idea were planted not in cosmology, but in the study of the most extreme objects in the universe, black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which is a measure of the information or disorder contained within it, is not proportional to its volume as one might expect, but to the surface area of its event horizon. This was a revolutionary clue. It suggested that all the information about everything that ever fell into a black hole was not lost inside its infinite density, but was somehow smeared and stored on its two-dimensional boundary. This finding helped resolve Stephen Hawking's famous black hole information paradox, which questioned whether information could be truly destroyed, a violation of quantum mechanics. The holographic principle emerged as a solution. Information is never lost, it is just encoded on a surface we cannot see. This concept was dramatically expanded upon by physicists Gerard T. Hooft and Leonard Susskind, who proposed that this might not just be a strange property of black holes, but a fundamental feature of the entire universe. The mathematics of string theory provided a powerful framework for this idea, suggesting that our three-dimensional spatial reality and everything within it could be entirely described by quantum processes happening on a distant, two-dimensional surface at the very edge of the cosmos. In this view, our universe is not a collection of things in a volume, but a tapestry of information painted on a surface. We are, in a very real sense, living inside a projection, much like the three-dimensional image that appears to float above a two-dimensional holographic sticker. To make this tangible, imagine watching a movie on an incredibly high-definition television screen. The screen itself is flat, just two dimensions, but the image it creates has depth, perspective, and the illusion of three-dimensional space. The actors seem to move toward you and away from you, but all that information, every detail of the scene, is contained within the flat, pixelated surface of the screen. The holographic principle suggests our universe operates in a similar way. The stars, planets, and even your own body are like the rich images on the screen, while the true, fundamental reality is the flat, informational code at the boundary of the universe. This isn't just a philosophical curiosity. It has profound implications for how we understand space, time, and the fundamental limits of reality. It suggests that there is a maximum amount of information that any region of space can contain, and that limit is defined by its surface area, not its volume. It's a theory that elegantly bridges the enormous gap between the world of the very large, governed by Einstein's gravity, and the world of the very small, ruled by quantum mechanics. By positing that the universe is fundamentally a quantum system of information on a boundary, the holographic principle offers a potential path toward a complete, unified theory of physics. It tells us that the cosmos might be the ultimate illusion, a magnificent and incredibly detailed hologram whose secrets are written on the surface of the void. But to truly understand the grand structure of everything we see today, we must rewind the cosmic clock to an almost unimaginably brief moment after the birth of the universe. This brings us to a theory that is as elegant as it is essential: cosmic inflation. Proposed by physicist Alan Guth in the early 1980s, inflation addresses some of the most perplexing questions left unanswered by the standard Big Bang model. Why does the universe, when we look in every direction, appear so remarkably uniform? And how did the vast cosmic structures like galaxies and clusters even begin to form? Inflation provides a stunningly simple yet powerful answer. A fraction of a second after the initial singularity, the universe experienced a period of hyper-fast, exponential expansion, ballooning from a subatomic speck to something astronomically larger in less time than it takes to blink. Before inflation, the observable universe was a tiny, compact region where quantum fluctuations were the dominant feature. This tiny region was so small that it had ample time to reach a uniform temperature and density, achieving a state of thermal equilibrium. Then inflation kicked in, driven by a peculiar state of energy field known as the inflaton. The fabric of space itself stretched at a rate far faster than the speed of light. This wasn't matter moving through space faster than light, which is forbidden, but the expansion of space itself, which has no such speed limit. In an almost infinitesimally short period, perhaps as brief as 10 to the power of negative 36 seconds, the universe expanded by a factor of at least 10 to the power of 26. To put that incomprehensible scale into perspective, it's like blowing up a single atom to the size of an entire galaxy instantly. This incredible growth spurt elegantly solves the horizon problem. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it is almost perfectly uniform in temperature, no matter which direction we point our telescopes. The problem is that these regions on opposite sides of the sky were never close enough to have exchanged heat and evened out their temperature under the old Big Bang rules. Light simply hasn't had enough time to travel between them. Inflation explains this by positing that these vastly separated regions were indeed once in intimate contact, part of that same tiny pre-inflationary patch that was then stretched across the entire cosmos, locking in that original uniformity across a vast volume. Furthermore, inflation provides a compelling explanation for the overall geometry of the universe. Observations tell us that the cosmos is incredibly flat on the largest scales, meaning that parallel lines stay parallel and the rules of Euclidean geometry we learned in school hold true. For the universe to be this flat, its density must be exquisitely fine-tuned to a critical value. The inflationary model naturally produces this flatness. Imagine taking a wrinkled piece of paper, a highly curved surface, and stretching it to an enormous size. Any small local wrinkles would be pulled taut, and the surface would appear increasingly smooth and flat. In the same way, the violent expansion of inflation stretched the fabric of space-time, smoothing out any initial curvature and driving the overall geometry of the observable universe toward perfect flatness. Perhaps most importantly, inflation doesn't just create a smooth and flat universe, it also provides the seeds for all future structure. Those tiny quantum fluctuations that were present in the primordial speck were not erased by the expansion. Instead, inflation stretched them to astronomical sizes, freezing them into the fabric of space-time as minute variations in density. These tiny ripples in the density of the universe became the gravitational seeds around which matter would later coalesce. Over billions of years, gravity amplified these slight overdensities, pulling in dark matter and gas to eventually form the first stars, the galaxies, and the magnificent cosmic web we observe today. Without those quantum seeds magnified by inflation, the universe would be a profoundly dull and empty place, a featureless sea of particles with no galaxies, no stars, and no us. The theory of cosmic inflation is more than just an add-on to the Big Bang. It is the pivotal chapter that explains how a chaotic, quantum beginning was transformed into the structured, observable cosmos we are now here to explore. What if the universe we perceive, with all its galaxies, stars, and laws of physics, isn't a fundamental reality at all, but rather an extraordinarily sophisticated simulation, much like an advanced video game? This is the core of the simulation hypothesis, a theory that has leapt from the pages of philosophy and science fiction into serious scientific and technological discussion. The idea was most famously formalized by philosopher Nick Bostrom at the University of Oxford. He breaks it down into a logical trilemma, suggesting that at least one of the following three propositions must be true. First, almost all civilizations at our level of technological development go extinct before becoming advanced enough to create realistic simulations. Second, any advanced civilization that does survive has absolutely no interest in running simulations of its ancestors. Or third, we are almost certainly living inside a computer simulation right now. The argument is that if even a tiny fraction of advanced civilizations were to run such simulations, the number of simulated minds would vastly outnumber the biological ones, making it statistically far more likely that we are among the simulated beings. This concept is made profoundly more relatable by our own rapid advancements in computing and virtual reality. Think about the video games of just a few decades ago, simple, blocky pixels moving across a screen. Today, we have fully immersive virtual worlds populated by millions of players, with graphics so realistic they can be mistaken for film. Artificial intelligence is beginning to create non-player characters that can hold convincing conversations. Now, project this technological trajectory forward a few thousand or even a million years. A civilization that has mastered its planet's resources and energy output could theoretically possess the computing power to simulate not just a room or a city, but an entire universe, complete with conscious beings who believe their reality is genuine. In this context, the hypothesis shifts from pure speculation to a plausible extrapolation of our own technological arc. This leads to a fascinating and fun question. If this is a simulation, could we ever find evidence of it? Some theorists suggest that potential glitches in the matrix might be observable in the weirdest corners of quantum mechanics. For instance, the principle that particles exist in a blur of probability until they are observed could be interpreted as a clever programming trick to save on computational resources. Why render something in perfect detail if no one is looking at it? The finite speed of light could be seen as a limit on the render distance of the simulation, preventing the system from being overloaded by having to display the entire infinite universe at once. Even the strange, discrete energy levels in atoms, which jump between states without existing in between, could be viewed as evidence of a pixelated reality operating on a fundamental resolution limit. While these aren't proof, they offer a playful lens through which to examine some of physics' deepest mysteries. Ultimately, the simulation hypothesis is less about providing a definitive answer and more about challenging our perception of reality itself. It forces us to confront profound philosophical questions about consciousness, existence, and what it truly means to be real. Whether we are lines of code in an alien computer or products of a natural universe, the quest for understanding remains our most human endeavor. The theory serves as a powerful reminder that our models of the cosmos are always evolving, and the next great discovery might not be about a new particle or force, but about the very nature of our existence. Now, just as the simulation hypothesis challenges the nature of reality, another theory aims to unify its very foundations, proposing a single, elegant framework to explain everything from the smallest particles to the vast cosmos. This brings us to one of the most ambitious and mathematically complex ideas in modern physics, string theory. At its heart, string theory offers a radical reimagining of what the universe is made of. For decades, the standard model of particle physics has described the fundamental building blocks of nature as point-like particles, electrons, quarks, and photons, with no size or internal structure. String theory proposes something far more beautiful, that at the most microscopic level, these aren't dots but incredibly tiny, vibrating loops of energy or strings. These strings are so small that if an atom were enlarged to the size of our solar system, a single string would be no larger than a tree on Earth. The magic of this idea lies in the vibration. Much like a single violin string can vibrate at different frequencies to produce a whole range of distinct musical notes, a low C, a high G, and everything in between, a fundamental string in space can vibrate in different modes. One specific pattern of vibration might make the string appear to us as an electron, with its specific mass and negative charge. A different, higher energy vibration might make that very same type of string manifest as a quark or a photon or even a graviton, the hypothetical particle that carries the force of gravity. In this stunning vision, all the different particles and forces we observe are not fundamentally different things. They are just different notes on the same cosmic instrument, all emanating from the symphony of vibrating strings. This elegant concept naturally leads to a monumental goal, the unification of all forces. For centuries, physics has sought a single theory that can describe the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces under one roof. Einstein spent his later years searching for such a unified field theory without success. The great challenge has been that gravity, described by Einstein's general relativity, operates beautifully on the scale of planets and galaxies, while the other three forces, described by quantum mechanics, rule the atomic and subatomic world. The two theories are mathematically incompatible, leading to nonsensical infinities when pushed to extremes, like the center of a black hole or the moment of the Big Bang. String theory smoothly incorporates gravity from the very beginning, offering a potential path to finally marry the world of the very large with the very small into a single, coherent theory of everything. However, this incredible promise comes with a fascinating and mind-bending requirement: extra dimensions. For the math of string theory to work consistently, it demands that space-time has more than the 3 dimensions of space and 1 of time that we experience every day. Most versions of the theory require a total of 10 or even 11 dimensions. This immediately raises an obvious question: if these dimensions exist, where are they? Why don't we see them? The leading explanation is that they are compactified or curled up into an exceedingly tiny, complex shape at every single point in space. Imagine a long, thin garden hose stretching far into the distance. From a distance, it appears to be a simple one-dimensional line, but if you get very close, you realize it has a second dimension, a circular cross-section going around its tube. In the same way, at every point in our familiar 3-dimensional space, there could be 6 or 7 extra spatial dimensions curled up into a fantastically small size, far too tiny for our instruments or our senses to detect. The geometry of these hidden dimensions is not arbitrary. They are theorized to be folded into intricate shapes known as Calabi-Yau manifolds. These are complex, multi-dimensional shapes that look like intricate gems or crumpled paper when visualized in 3 dimensions, and their specific geometry is everything. The way a Calabi-Yau manifold is folded determines the vibrational patterns that are possible for the strings residing within it. In essence, the shape of these unseen dimensions dictates the laws of physics in our visible universe. One specific fold might produce a universe with our exact physical constants and particle properties, while a slightly different fold would create a universe with completely different rules, perhaps where atoms are unstable or gravity is repulsive. This provides a potential string theoretic explanation for the fine-tuning problem, and even connects to the multiverse concept, as each different compactification could correspond to a different universe bubble in a vast landscape of possibilities. Despite its profound beauty and theoretical promise, string theory faces a significant hurdle: a complete lack of experimental verification. The energy levels required to directly probe the scale of strings or to uncurl these extra dimensions are far beyond the capabilities of any particle accelerator we could ever hope to build, placing them trillions of times beyond our current reach. For now, and perhaps forever, string theory remains a magnificent and powerful mathematical framework, a compelling glimpse into how the universe might operate at its most fundamental level. It represents the ultimate exercise in human curiosity, using the language of mathematics to ask what the universe is truly made of, and daring to imagine a reality far stranger and more wonderful than we ever thought possible. Yet for all its mind-bending implications, the many worlds interpretation is grounded in a very real and well-documented quantum phenomenon: superposition. This is the bizarre principle that, until it is measured, a particle like an electron doesn't have a definite property like a specific position or spin. Instead, it exists in a blurred state of all possible values simultaneously. In the classic Copenhagen interpretation, it's the act of observation itself that forces this probability wave to collapse into a single, definite outcome. Everett's genius was to remove the observer from this special role. He proposed that the wave function doesn't collapse at all. Instead, the observer simply becomes entangled with the system. When you look at that electron to measure its position, your own state becomes linked with its superposition. In one branch of reality, you see the electron in one location. In another, equally real branch, a version of you sees it in a different spot. Both outcomes are realized, but the yous are now forever separated into different, non-communicating worlds. This process of separation is understood through a concept called quantum decoherence. Think of it as the mechanism that keeps these parallel worlds from interfering with one another. When two quantum systems interact like an atom and a measuring device, their wave functions become entangled. But this delicate quantum correlation is incredibly fragile and is quickly destroyed by interactions with the surrounding environment, a process that spreads at the speed of light. This rapid decoherence effectively severs the connection between the newly created branches, preventing any information or influence from passing between them. It's the reason why we don't experience these splits in our everyday lives. Each branch evolves on its own, completely unaware of the countless others splitting off every instant. Decoherence provides the how for the many worlds interpretation, explaining the mechanism that makes the branching not just a philosophical idea but a dynamic physical process. To visualize this, picture not a tree with solid branches but an endlessly dividing river of time. At every nanosecond, at every point where a quantum event has more than one possible outcome, the river forks into separate streams. Each stream is a complete and consistent universe carrying forward a unique version of history. In one stream, a cosmic ray missed a key cell in your ancestor's body, and your family line continued. In the stream right next to it, that cosmic ray hit its mark and you never existed. In one world, you turned left on your way to work this morning. In another, you turned right and had a completely different day. The number of these branches is truly infinite, encompassing not just every possible outcome of every quantum event, but every possible permutation of those outcomes across all of time and space. It is a cosmos of unparalleled richness, where every story that can be told is being told somewhere in its own self-contained reality. This interpretation, while resolving the paradoxes of measurement, opens up a profound set of new questions about identity and probability. If every possible outcome occurs, what does it even mean to talk about the odds of something happening? Proponents answer that probability is about the perspective of the observer. From your point of view, before a quantum event occurs, you are destined to split into multiple copies. The probability of a particular outcome is essentially the measure of how many of your future selves will experience that result. For a 50-50 quantum coin flip, you will split into two equally valid versions of yourself. The you in this world experiences heads and the other you experiences tails. Both are certain of their outcome, yet from the prior perspective, there was only a 50% chance of you ending up in this specific branch. It's a dizzying redefinition of chance that places the individual at the center of an infinite, branching multiverse of their own making. While the multiverse and many worlds interpretations deal with the grand architecture of reality, and string theory aims for a final unification, there is one cosmic component that is actively shaping the destiny of the entire universe right now. It's a force so dominant that it makes up nearly 70% of all the energy in the cosmos, yet we know almost nothing about its true nature. This brings us to a concept that was once dismissed as a physicist's embarrassing mistake, only to be resurrected as perhaps the most important discovery in modern cosmology: the cosmological constant, our leading candidate for the mysterious dark energy. The story begins with Albert Einstein himself. In 1917, while applying his new theory of general relativity to the universe as a whole, he encountered a problem. His equations kept predicting that the universe should either be expanding or contracting, which contradicted the prevailing scientific wisdom of the time that the cosmos was static and eternal. To force his equations into this static model, Einstein introduced a fudge factor, a term represented by the Greek letter lambda. This cosmological constant was a kind of repulsive energy, a negative pressure inherent to the fabric of empty space itself, which could precisely balance the inward pull of gravity on a cosmic scale, holding the universe in a steady state. Later, when Edwin Hubble's observations conclusively proved that the universe was indeed expanding, Einstein famously discarded the cosmological constant, calling it his biggest blunder. He had missed the chance to predict the expanding universe, all because of an unnecessary term he had inserted. The idea lay dormant for decades until the late 1990s, when two independent teams of astronomers made a discovery that would turn cosmology upside down. They were measuring the distances to extremely far-away Type 1a supernova, which are stellar explosions that all have roughly the same intrinsic brightness. By comparing how bright these standard candles appeared to be with how bright they actually are, astronomers can calculate their distance with great accuracy. Furthermore, by analyzing the redshift of their light, they can determine how much the universe has expanded since the moment that light was emitted. The teams expected to find that the expansion of the universe was slowing down over time, as the collective gravity of all matter pulls back on the initial momentum of the Big Bang. To their complete astonishment, they found the opposite. The most distant supernova were dimmer than expected, meaning they were farther away than anyone had predicted. The only explanation was that the expansion of the universe wasn't slowing down at all, it was speeding up. Some mysterious repulsive force, now called dark energy, was overcoming gravity and pushing galaxies apart at an ever-increasing rate. The simplest and most elegant explanation for this accelerating expansion was the triumphant return of Einstein's cosmological constant. In this modern view, it is not a mathematical fudge factor but a fundamental property of the vacuum of space. According to quantum physics, empty space is not truly empty. It is a seething, bubbling foam of virtual particles constantly flickering in and out of existence. This quantum activity is theorized to endow every cubic centimeter of space with a tiny, constant energy density. The key here is that this energy density does not dilute as the universe expands. As more space comes into existence, more of this repulsive energy is created with it. This means that while the density of matter and radiation thins out over time, the density of dark energy remains constant, allowing its gravitational influence to eventually dominate and begin driving an accelerated expansion. This model, where lambda represents dark energy, is the L in the lambda-CDM model, which is the current standard model of Big Bang cosmology, describing a universe made of dark energy, cold dark matter, and ordinary matter. However, this elegant solution comes with what is perhaps the most embarrassing problem in all of theoretical physics, the cosmological constant problem. When physicists attempt to calculate the expected value of this vacuum energy using quantum field theory, they get a number that is absurdly, incomprehensibly large, about 120 orders of magnitude too big. That's a 1 followed by 120 zeros, a value that large would have ripped the universe apart in a fraction of a second after the Big Bang, tearing atoms to shreds before stars or galaxies could ever form. The fact that the observed value of dark energy is so miraculously small, yet not zero, is a fine-tuning problem that makes the conditions for life seem almost trivial by comparison. Why is the cosmological constant so exquisitely tuned to a value that allows for a universe like ours? Some physicists suggest this might be evidence for the Anthropic Principle and a vast multiverse, where we simply reside in one of the rare bubbles where the value of lambda is set just right. Others believe it points to a fundamental flaw in our understanding of quantum gravity or vacuum energy, waiting for a deeper theory to provide the answer. This tiny number represents the greatest disconnect between theory and observation in all of science, a silent, pervasive mystery that holds the ultimate fate of the entire cosmos in its balance. But if we shift our gaze from the grand fate of the cosmos to the familiar space of our own solar system, we find a mystery unfolding right in our celestial backyard, a detective story that suggests our planetary family might still have a missing member. This is the Planet 9 hypothesis, a compelling theory proposing that a large, undiscovered world is lurking in the frozen darkness far beyond Neptune, its gravitational pull subtly orchestrating the orbits of small, icy bodies in the distant Kuiper belt. The evidence for this hidden world comes not from a direct glimpse, but from the collective odd behavior of a group of extreme trans-Neptunian objects. These are small, icy worlds that orbit the Sun at astounding distances, taking thousands of years to complete a single journey. Astronomers studying their paths began to notice something peculiar. A specific cluster of these objects, with orbits that take them incredibly far from the Sun, share a striking and highly unlikely similarity. Their orbits are all tilted in the same direction, and their points of closest approach to the Sun, their perihelia, are all grouped together in space. For this to happen by random chance is astronomically improbable, like rolling 10 dice and having them all land on the same number multiple times in a row. The most elegant explanation is that a massive, unseen object is herding them, its persistent gravitational influence keeping their orbits aligned over billions of years. Based on the precise way these distant objects are clustered, astronomers Konstantin Batygin and Mike Brown have calculated the likely properties of this potential perturber. The hypothetical Planet 9 is estimated to have a mass about 5 to 10 times that of Earth, which would make it a super-Earth or a mini-Neptune, a class of planet common around other stars but curiously absent from our own solar system. Its orbit would be immense and highly elliptical, taking it on a long, slow journey around the Sun. At its closest approach, it might come within 200 to 300 astronomical units from the Sun. But at its most distant point, it could venture out to a staggering 600 to 1,000 astronomical units. To put that in perspective, 1 astronomical unit is the distance from the Earth to the Sun. Pluto, by comparison, orbits at an average of about 40 astronomical units. This proposed world exists in a realm of perpetual twilight, so far away that the Sun would appear as nothing more than an exceptionally bright star in its black sky. The search for this elusive world is one of the great modern hunts in astronomy, a painstaking process of scanning vast tracts of the sky for a faint, slow-moving dot. Because its orbit is only roughly constrained, astronomers have a massive haystack of space to sift through. The task is further complicated by its incredible distance. Any sunlight reflecting off its surface would be incredibly faint, right at the edge of what our most powerful telescopes can detect. Projects like the Subaru telescope on Mauna Kea and the Vera C. Rubin Observatory, which is set to begin operation soon, are leading this charge. They methodically image large sections of the sky, looking for that one pixel that moves just a tiny amount against the backdrop of fixed stars over nights, weeks, or even months. It is a testament to patience and technology, a cosmic game of hide and seek where the seeker isn't even entirely sure what they're looking for. Beyond solving an orbital puzzle, the discovery of Planet 9 would have profound implications for our understanding of how our solar system formed and evolved. Its existence would likely be a relic of a dramatic and violent past. One leading theory suggests it could be a primordial planet that formed much closer to the Sun, alongside the other giants, only to be violently flung out into its current distant orbit during the solar system's chaotic early days when gravitational interactions between the young planets were common. Alternatively, an even more exotic possibility exists that the Sun could have captured a free-floating rogue planet that was drifting through interstellar space, gravitationally pulling it into a permanent orbit. Finding Planet 9 wouldn't just be about adding a new line in a textbook. It would provide a living piece of evidence from the solar system's infancy, offering a new narrative for our own cosmic origin story, and finally explaining why the outer solar system looks the way it does. This idea offers a surprisingly hopeful answer to one of the most haunting questions in science, the Fermi paradox. If the universe is so vast and ancient, teeming with potentially habitable worlds, then where is everybody? The zoo hypothesis proposes a peaceful and even benevolent explanation. It suggests that advanced extraterrestrial civilizations are not only aware of us, but have deliberately chosen to avoid contact, placing our planet under a form of cosmic quarantine or observation. In this view, Earth is a designated wilderness area or a protected cultural preserve, and humanity is a developing species to be studied from a respectful distance, much like anthropologists observing an uncontacted tribe in the Amazon. The primary rule of this galactic society would be a strict non-interference policy, a prime directive designed to allow our civilization to evolve naturally, free from the shock and potential cultural collapse that would come from knowing we are not alone. This theory completely reframes the purpose of programs like SETI, the search for extraterrestrial intelligence. Instead of a failure, the Great Silence could be seen as a sign of success. Our radio telescopes and optical arrays haven't found anything not because there's nothing to find, but because we are listening for a transmission that the galaxy's established residents are ethically bound not to send. Our efforts might be the equivalent of a child in a zoo shouting into a walkie-talkie, hoping the zookeepers will answer, while the adults simply watch with quiet interest from behind a one-way mirror. This perspective suggests that contact might only occur on their terms, at a specific milestone in our development, perhaps when we as a species achieve a certain level of technological maturity, solve our own global conflicts, or collectively demonstrate a willingness to join a wider cosmic community. Until that time, we are essentially in a state of cosmic childhood, being given the space to grow up. The ethical considerations behind such a policy are profound and mirror our own debates about conservation and cultural preservation. A civilization capable of such restraint would likely possess a deep wisdom born from its own historical mistakes, understanding that forced contact can be a form of cultural imperialism with devastating consequences. They might look back on their own past and see the damage caused by their own first encounters with other species, leading them to establish this galaxy-wide standard. The hypothesis presents a vision of a mature, coordinated galactic community that values biological and cultural diversity above all else, seeing each emerging world as a unique and irreplaceable experiment in consciousness worthy of protection. This stands in stark, chilling contrast to more ominous solutions to the Fermi paradox, most notably the dark forest theory. That model imagines the cosmos as a vast, dangerous woodland where every civilization is a hidden hunter, terrified of revealing its location. In the dark forest, any newly discovered civilization is not a wonder to be preserved, but a potential threat to be immediately eliminated. The first species to announce its presence is the first to be targeted. This results in a universe where everyone is listening, but no one is broadcasting, a state of perpetual and silent paranoia. The zoo hypothesis and the dark forest theory represent two polar opposite visions of cosmic sociology, one founded on a principle of ethical observation and patience, the other on a ruthless principle of survival at any cost. One offers a future of eventual welcome into a galactic federation. The other promises only eternal isolation or inevitable annihilation. The silence we hear could be either the quiet of a museum or the quiet of a hunter's blind, and we have no way of knowing which until we finally get an answer. But what if the very ingredients for life here on Earth didn't originate on our planet at all? This brings us to a theory that completely reimagines our cosmic origins, panspermia. The core idea is both simple and profound. Life, or at least its fundamental building blocks, is not confined to a single world but is a widespread phenomenon throughout the universe, distributed by natural celestial taxis like asteroids, comets, and cosmic dust. In this view, Earth may not be a unique cradle of life, but simply a fertile garden where seeds sown from the depths of space found the perfect conditions to take root and flourish. The theory gains significant credibility from two powerful lines of evidence found right here at home. The first is the discovery of extremophiles, incredibly resilient microorganisms that thrive in conditions once thought to be utterly incompatible with life. Scientists have found bacteria living in boiling hot geothermal vents at the bottom of the ocean, frozen solid within ancient Antarctic ice, in highly acidic lakes, and even buried deep within radioactive rock. These tiny life forms demonstrate that biology is far hardier than we ever imagined, capable of surviving the kinds of extreme temperatures, pressures, and radiation levels that would characterize a long-duration journey through the vacuum of space aboard a rocky asteroid. If a microbe can hibernate inside a rock for millions of years on Earth, it's not a huge leap to suggest it could survive an interstellar voyage. Secondly, astronomers have consistently found a rich inventory of organic molecules throughout the cosmos, the very precursors to life as we know it. Sophisticated telescopes have identified complex carbon-based compounds, including amino acids and sugars, swirling within vast interstellar gas clouds, embedded in the tails of comets, and even on the surfaces of asteroids. In 2019, the Japanese Hayabusa 2 mission successfully collected samples from the asteroid Ryugu and found them to contain uracil, one of the 4 core nucleobases that form the backbone of RNA. This discovery provides a direct, tangible link, showing that the chemical letters needed to write the code of life are not only present out there but are being delivered to planets throughout the galaxy as a matter of course. The universe, it seems, is preloaded with the ingredients for biology. This natural process gets even more intriguing when we consider the possibility of it being intentional. This concept is known as directed panspermia, a hypothesis first seriously proposed by Nobel Prize-winning biochemist Francis Crick. He pondered whether an advanced extraterrestrial civilization, perhaps facing its own impending doom, might have deliberately sent out robotic spacecraft or specially designed capsules loaded with microbial life to seed habitable planets across the galaxy. This wouldn't be an act of war, but one of preservation or even generosity, a way to ensure that the flame of life, their biological heritage, continues to burn somewhere in the cosmos long after their own star has faded. In this scenario, we and every other living thing on Earth could be the distant descendants of a biological project started by an intelligence we have yet to meet, making every one of us a form of living alien artifact. Perhaps the most compelling argument for panspermia, directed or not, is how it elegantly solves a timing problem in our own planet's history. Geological evidence shows that life appeared on Earth astonishingly early, mere hundreds of millions of years after the planet's surface cooled and solidified enough to hold liquid water. In the grand 4.5 billion-year timeline of Earth, this is a blink of an eye. For life to have arisen completely independently from non-living chemistry in such a short window is statistically challenging for some scientists. Panspermia offers an elegant solution. Life didn't have to start from absolute scratch here. Instead, the process may have begun millions or even billions of years earlier around another star, and our planet was simply the lucky recipient of a well-timed biological delivery, giving evolution a massive head start. This doesn't answer the ultimate question of how life began in the first place, but it does push that profound mystery out into the wider galaxy, suggesting that when we finally find other life, we may all be part of the same vast, interconnected family tree. Now we plunge into one of the most profound and heated debates in all of theoretical physics, a conflict that strikes at the very heart of our understanding of reality. This is the black hole information paradox, a puzzle that has pitted two of our most successful scientific theories against each other in a battle where something has to give. On one side, we have Einstein's general relativity, our magnificent description of gravity and the large-scale structure of the universe. On the other, we have quantum mechanics, the incredibly accurate rulebook for the subatomic world. For decades, they coexisted by simply operating in different domains. But at the edge of a black hole, the place where gravity is at its most extreme and quantum effects cannot be ignored, these two titans of physics collide, and the result is a paradox that threatens to undermine the very foundations of science. To understand the problem, we first have to understand what we mean by information. In physics, information isn't just data. It refers to the specific, unique quantum state of every particle that makes up an object. It's the complete blueprint that distinguishes one collection of atoms from another. It's the difference between the quantum states that make up a diamond and those that make up a pile of ash. A cornerstone principle of quantum mechanics is that this information can never be truly destroyed. It can be scrambled, changed, and made incredibly difficult to read, but it must be conserved. It's a fundamental tenet upon which all of modern physics is built. Enter the black hole, the ultimate rebel. According to general relativity, a black hole is defined only by its mass, electric charge, and spin. This is known informally as the no-hair theorem. If you throw a grand piano, a library of encyclopedias, or a cloud of radioactive gas into a black hole, the theory claims the black hole would respond in exactly the same way. It would simply get a tiny bit more massive. All the intricate information about what made those objects unique, the composition of the piano's wood, the words in the books, the atomic structure of the gas seems to be completely and irretrievably erased from our universe, violating the sacred quantum law of information conservation. The plot thickened dramatically when Stephen Hawking applied quantum theory to the space just outside a black hole's event horizon. He discovered that black holes aren't completely black. Due to weird quantum fluctuations, they slowly emit a faint glow of radiation, now famously known as Hawking radiation. This process causes the black hole to gradually lose mass and over eons evaporate completely. Here's the crux of the paradox. Hawking's original calculations showed that this radiation is purely thermal. It's random noise like the heat radiating from a stove, and it contains no information whatsoever about what fell into the black hole. So when the black hole finally evaporates into a brief puff of this random radiation, the information about everything it ever consumed is seemingly lost forever. Poof, gone. This presented physics with an impossible choice. Either our understanding of quantum mechanics is wrong and information can be destroyed, or our understanding of general relativity at the event horizon is incomplete. For decades, this was the stalemate. Then, a potential solution emerged from a concept we touched on earlier, the holographic principle. This idea suggests that all the information about everything within a three-dimensional volume of space, including everything that falls into a black hole, is actually encoded on its two-dimensional boundary, the event horizon. Imagine the event horizon as a super-dense cosmic hard drive. When an object falls in, its information isn't destroyed. It's smashed and stored as a complex pattern on this surface, like a pixelated image. Then, as Hawking radiation is emitted, it slowly and subtly carries that encoded information back out into the universe. The radiation only appears random to a casual observer. Upon incredibly detailed inspection, it would contain the entire history of the black hole's diet. This would satisfy quantum mechanics and save the conservation of information, but it requires a radical rethinking of where and how reality truly exists. However, this holographic solution created a new, equally baffling problem often called the firewall paradox. If information is slowly leaking out over the black hole's entire lifetime, then the event horizon cannot be the smooth, uneventful space that general relativity predicts. Instead, it would have to be a seething, violent wall of energy, a firewall, that would instantly incinerate anything crossing it. This directly contradicts Einstein's principle of equivalence, which states that an observer falling into a black hole should notice nothing unusual as they cross the event horizon. It should be locally unremarkable. So we're stuck again. Either information is lost, which breaks quantum mechanics, or the event horizon is a deadly firewall which breaks general relativity. This has led to some of the most creative and mind-bending ideas in modern physics, like the ER equals EPR conjecture proposed by physicists Leonard Susskind and Juan Maldacena. This elegant idea suggests that the fabric of spacetime itself might be connected by quantum entanglement. In simple terms, when a particle falls into a black hole, it might become instantly connected via a microscopic wormhole, an Einstein-Rosen bridge, to one of the Hawking radiation particles leaving the black hole. This invisible link would provide a secret tunnel for information to escape, preserving it without the need for a destructive firewall. It's a proposal that beautifully weaves together the concepts of quantum connection and the geometry of spacetime, suggesting that the universe might be far more interconnected than we ever dreamed. Ultimately, the black hole information paradox is far more than an abstract theoretical puzzle. It is a crucial stress test for our quest to find a unified theory of quantum gravity. Whichever theory, be it string theory, loop quantum gravity, or something entirely new, that successfully resolves this paradox will have proven that it can truly reconcile the worlds of the very large and the very small. It forces us to ask what really happens at the edge of reality and challenges our most basic assumptions about space, time, and information itself. Solving it wouldn't just tell us what happens to stuff that falls into a black hole, it would reveal the deepest operating rules of the universe. While the standard Big Bang model paints a picture of a singular beginning and an eventual cold, lonely end, another theory offers a far more dramatic and eternal vision for the cosmos. This is the cyclic model, which proposes that our universe is not a one-time event, but merely the latest chapter in an endless, timeless cycle of cosmic death and rebirth. In this view, the Big Bang was not the absolute beginning, but a violent transition from a previous era, and our universe's ultimate fate is not to fade into darkness, but to be reborn in a fiery collision that seeds the next cycle. The roots of this modern cyclic model are deeply entwined with string theory and its concept of branes or membranes. These are not just two-dimensional surfaces, but dynamic objects that can exist in many more dimensions. The theory suggests our entire universe might be confined to a three-dimensional brane, floating like a vast, flat sheet in a higher dimensional space called the bulk. Crucially, there could be another universe, another brane, floating on a parallel course in this higher dimensional reality. The cyclic model proposes that the Big Bang was caused by a collision between our brane and this neighboring one. This collision would have released an immense amount of energy, flooding our brane with radiation and matter and effectively resetting the cosmic clock, creating what we observe as the hot, dense beginning of our universe. This leads to a profound new timeline. Instead of a linear progression from a single beginning to a final end, the cyclic model describes a never-ending loop. Each cycle begins with a bang caused by a brane collision. The universe then expands and evolves for trillions of years, with galaxies forming, stars living and dying, and eventually, dark energy driving a rapid acceleration that stretches the universe into a vast, cold, and nearly empty state. But then, rather than ending in silence, the cycle turns. The mysterious nature of dark energy in this model evolves, eventually becoming an attractive force that pulls the two branes back together across the higher dimensional bulk. They accelerate toward each other until bang, another collision, another universe is born from the ashes of the old one, and the entire process begins anew. In this vision, time has no true beginning and no final end. There is only the eternal rhythm of creation and destruction. A key piece of evidence that could support this radical idea might be hidden in the oldest light we can see, the cosmic microwave background. This faint afterglow from the early universe is remarkably uniform, but it contains tiny, fossilized fluctuations in temperature. The standard inflationary model predicts a very specific pattern for these fluctuations. Some versions of the cyclic model, however, predict that a brain collision could leave a different, distinctive imprint on this light, such as specific patterns of gravitational waves or certain asymmetries in the temperature map. While the current data from telescopes like Planck largely supports inflation, scientists are meticulously analyzing every detail, searching for any anomaly that might hint at a pre-Big Bang event, a cosmic fingerprint from a previous cycle. The implications of this model are staggering, completely redefining concepts of beginnings and endings. It elegantly sidesteps the philosophically troubling question of what existed before the Big Bang. There was no before in a linear sense, there was only the previous cycle of the universe. It also offers a new perspective on the fate of the cosmos. The heat death of the universe is no longer a final, eternal silence, but merely a phase, a necessary cooling off period before the next great explosion of life and complexity. It suggests that the universe itself may be immortal, undergoing an infinite series of regenerations, each one potentially giving rise to new galaxies, new stars, new planets, and perhaps new life. It is a vision of the cosmos that is both terrifying in its violence and beautiful in its endless capacity for renewal. While string theory adds extra dimensions to reality in its quest for unification, another brilliant school of thought takes a completely opposite approach, proposing that the key to quantum gravity lies not in adding anything new, but in rewriting the very definition of space and time. This is loop quantum gravity, a formidable rival to string theory that dares to suggest that space itself is not a smooth, continuous backdrop, but is instead woven from a fabric of finite, discrete loops. Imagine the fabric of the cosmos not as an infinitely divisible sheet, but as the most intricate tapestry ever made. In this view, space is composed of a network of incredibly tiny, one-dimensional loops woven together at their intersections. These loops are unimaginably small, existing at the Planck scale, which is about 10 to the negative 35 meters. You could pack more of these loops into a single cubic centimeter than there are cubic centimeters in the entire observable universe. The key here is that these loops are the fundamental building blocks. You cannot divide space into anything smaller. This means space is not continuous but granular or quantized, much like a digital photograph is made of individual pixels. The picture of space appears smooth from a distance, but if you could zoom in with infinite precision, you would eventually see its discrete, pixelated nature. This radical rethinking of spacetime's architecture provides a stunning solution to one of the most vexing problems in physics, the singularity. In Einstein's general relativity, singularities are points of infinite density and curvature where the laws of physics completely break down. They lurk at the center of black holes and mark the beginning of the universe in the Big Bang. Infinite values are a major red flag for physicists, signaling that a theory is incomplete. Loop quantum gravity naturally eliminates these infinities because its granular structure prevents matter and energy from being compressed into an infinitely small point. There's simply a smallest possible volume, a fundamental pixel of space. When matter is compressed to this extreme limit, the loops of spacetime push back with a powerful repulsive force, preventing a true singularity from ever forming. This leads to one of the theory's most breathtaking predictions, the Big Bounce. If the Big Bang wasn't a true singularity, then what was it? Loop quantum gravity suggests it was not the absolute beginning of everything, but a monumental transition from a previous phase of the universe. In this model, a prior universe very similar to our own eventually succumbed to its own gravity and began to contract. As it collapsed, the density and temperature soared to incredible levels, but just as it was about to reach the point of infinite density, the repulsive force generated by the quantized spacetime loops kicked in. This force became so powerful that it overcame the crush of gravity, causing the universe to bounce back outwards in a massive, explosive rebound. What we call the Big Bang was in fact this moment of cosmic rebirth. This paints a picture of a cyclical universe, potentially going through an endless series of expansions, contractions, and bounces, each one lasting perhaps trillions of years. The implications of this are truly profound. It completely redefines our concept of time and creation. There is no need for a mysterious genesis from nothing. The universe could be eternally evolving through these cycles. Each bounce would effectively reset the cosmic clock, erasing much of the information from the previous cycle, while seeding the new one with a hot, dense state primed for expansion. It offers an elegant alternative to the idea of a single, linear timeline with a definitive start and a potentially cold end, suggesting instead that the cosmos is immortal, perpetually recycling itself in the most dramatic way imaginable. While the mathematics of loop quantum gravity is exceptionally complex, its core promise is a universe built from a tapestry of tiny loops, forever avoiding the pitfalls of infinity and offering a majestic, cyclical vision of cosmic history. This brings us to a concept that is as profound as it is contentious, a principle that directly confronts the very reason we are here to ask these questions in the first place. We've explored how the universe's fundamental constants appear perfectly fine-tuned for life, a puzzle that has led us to theories like the multiverse. But there is another, more mind-bending perspective that turns the question entirely on its head. This is the Anthropic Principle, the simple yet staggering idea that the universe must be compatible with conscious life, because if it weren't, we wouldn't be here to notice. It's a statement that seems almost too obvious, yet its implications ripple through cosmology, philosophy, and our entire understanding of reality. The principle is most commonly discussed in two distinct forms, often called the weak and strong anthropic principles. The weak version is a straightforward selection effect, a statement about our own observational position. It notes that we necessarily find ourselves in a place and time in the universe where the conditions are right for our existence. We couldn't observe a universe that was incompatible with life, just as a fish couldn't observe a world without water. This weak principle is largely uncontroversial. It's a logical truism that helps explain why our planet is ideally situated for life, why we emerged billions of years after the Big Bang once the necessary heavy elements were forged in stars, and why we don't find ourselves in the empty, radiation-drenched void between galaxies. It's a filter for our observations. The strong version of the principle, however, ventures into far more speculative and debated territory. It suggests that the universe seems fine-tuned for life because in some sense it had to be. This isn't just about our location within a universe, but about the fundamental laws and constants of the universe itself. Proponents of the strong view argue that the existence of conscious observers is not a happy accident but a necessary outcome, perhaps because consciousness plays a fundamental role in the actualization of reality. This stronger interpretation often brushes up against ideas in quantum mechanics, where the act of observation is theorized to collapse probability waves, and even philosophy, implying a universe that seems almost designed with the eventual emergence of mind as a key ingredient. The Anthropic Principle finds its most powerful and scientifically robust application when paired with the Multiverse Theory. On its own, the incredible unlikelihood of our universe's balance can feel like a miracle waiting for an explanation. The multiverse provides that explanation through a colossal statistical sample size. If an infinite or near infinite number of universes exist, each with randomly determined physical constants, then it is no longer surprising that at least one universe turned out just right. We shouldn't be amazed that we live in a habitable universe. We must live in a habitable universe. The Anthropic Principle is the reason we find ourselves in this particular bubble, and not one of the countless others where stars never ignited or atoms never formed. In this context, it transforms from a philosophical curiosity into a practical tool for testing theories in cosmology. Yet, for all its explanatory power, the Anthropic principle is often met with strong criticism. Detractors argue that it can be a conversation stopper, a clever-sounding way to avoid seeking a deeper, more physical explanation for the universe's fine-tuning. If we simply chalk up every cosmic coincidence to, well, otherwise we wouldn't be here, we might become complacent and stop looking for a more fundamental theory, perhaps one that predicts why the constants must have the values they do. To some, it feels like a cop-out, a retreat from the traditional goal of science, which is to find active, causal mechanisms rather than passive, observational constraints. It can be seen as resigning ourselves to a universe of incredible luck rather than one of elegant, underlying order. This tension lies at the heart of its provocative nature. Is the Anthropic principle a profound insight into the nature of reality and our place within it? Or is it merely a tautology, a statement that is true by definition but ultimately uninformative? The answer likely depends on how it is applied. Used responsibly, it is an essential lens that corrects our observational biases and helps guide our theories toward those that can naturally account for our existence. Used recklessly, it could be invoked to explain away any problem without offering testable predictions. It forces us to walk a fine line, reminding us that we are not passive observers of an objective reality, but active participants whose very existence is inextricably linked to the cosmos we are trying to understand. It is the ultimate reminder that in the grand quest to decode the universe, we must also decode our own role in the story. Now, this brings us to a concept that is both a chilling answer to the Fermi paradox and a stark warning for our own species. We call it the Great Filter. The premise is as simple as it is terrifying. The reason the galaxy appears so silent might be that there exists some kind of cosmic bottleneck, an evolutionary or technological hurdle so immense that it prevents virtually every single civilization from ever achieving interstellar travel or communication. The Great Filter is the reason the universe isn't teeming with life. It's the unseen barrier that stops it in its tracks. This idea forces us to confront a deeply unsettling question. Where is this filter located in the grand timeline of a civilization's development? Is it safely behind us, a challenge we've already miraculously overcome? Or is it still ahead, a looming catastrophe that we have yet to face and that may ultimately spell our end? The answer to this question holds profoundly different implications for humanity's future and our place in the cosmos. Let's first explore the possibility that the Great Filter is in our past. This is the more optimistic, though still humbling, scenario. It suggests that the step from non-life to life, the event of abiogenesis, might be astronomically rare. While we've found the building blocks of life everywhere in the cosmos, the actual leap from a soup of organic molecules to a self-replicating organism capable of evolution might be a fluke of near impossible odds. We might be the only game in town, or at least in this galactic neighborhood, simply because we were the only ones to win that first critical lottery. Other potential past filters could include the development of eukaryotic cells, which took over 2 billion years to emerge on Earth after the first simple prokaryotes, or the jump to complex multicellular organisms. Each of these evolutionary milestones represents a daunting barrier that most potential life-bearing worlds might never cross. However, a more disturbing and perhaps more probable answer is that the Great Filter lies in our future. This view suggests that the transition from a species that has mastered its planet to one that becomes a stable, multi-planetary civilization is the stage where nearly everyone fails. The most commonly cited future filter is self-annihilation through advanced technology. The moment a civilization discovers the power locked within the atom, it simultaneously gains the keys to its own destruction. Nuclear war is the classic example, but the potential filters are growing more numerous and sophisticated. We might engineer a supervirus that escapes our control, create a runaway nanotechnology that consumes the biosphere in a grey goo scenario, or develop an artificial superintelligence whose goals are not aligned with our own survival. The filter may not be a single event, but a whole period of existential risk that emerges from the very tools we create to propel ourselves forward. There's another, more cosmic possibility for a future filter: the idea that the universe itself is inherently dangerous for advanced life. Perhaps every civilization, upon reaching a certain level of technological maturity, inevitably discovers something: a new energy source, a physics experiment, a deeper understanding of reality that is catastrophically unstable. They might accidentally trigger a vacuum decay event, a catastrophic phase transition in the fabric of space-time that spreads at the speed of light, erasing not just their world but potentially altering the fundamental constants of the universe in an expanding bubble of destruction. Or they might discover that interstellar travel itself is far more perilous than we imagine, filled with unforeseen hazards like dense fields of interstellar dust or gamma-ray bursts that regularly sterilize large regions of the galaxy. In this view, space isn't a welcoming ocean waiting to be sailed, it's a minefield. The profound and sobering implication of the great filter theory is that it turns the Fermi paradox from a curiosity into an urgent diagnostic tool for our own civilization. The eerie silence we observe is not necessarily a promise of future companionship, but potentially a graveyard of countless civilizations that rose and fell before they could ever make their presence known. If the filter is ahead of us, then every day we survive without triggering our own extinction is a day we beat the odds. Our continued existence becomes a fragile, precious thing, and our most important mission shifts from seeking out others to ensuring we do not become yet another silent data point in the galaxy's great archive of failed species. The great filter theory doesn't just ask why we're alone. It demands that we look in the mirror and ask the most critical question of all: are we next? While black holes represent the ultimate cosmic sinkhole, a one-way street into oblivion, what if the equations of general relativity also allow for the exact opposite? Enter the white hole, a theoretical beast that is precisely the reverse of its dark cousin. Where a black hole's event horizon is a point of no return from which nothing can escape, a white hole would possess a horizon from which nothing can enter. It would be a cosmic gusher, violently expelling matter and energy into the universe in a process that is the exact time reversal of a black hole's formation. The mathematics of Einstein's field equations are time-symmetric, meaning they work just as well if you run the clock backwards. And this is where the concept of a white hole emerges as a valid, if exotic, solution. Imagine a black hole in Rewind. Instead of a star collapsing forever, you would see a fountain of energy and particles erupting from a single point, a big bang on a much smaller scale. It's a mesmerizing idea, but the catch is that white holes are thought to be incredibly unstable if they can form at all. The second law of thermodynamics, which dictates that disorder always increases, seems to forbid such a reversal of a black hole's natural evolution. Pouring milk out of a glass is easy, getting it to spontaneously jump back in is not. Most physicists consider white holes to be mathematical curiosities rather than physical realities, but they remain a fascinating testament to the strange symmetries hidden within Einstein's work. This exploration of distorted spacetime leads us to an even more alluring concept, the wormhole, often called an Einstein-Rosen bridge after the physicists who first described them. A wormhole is theorized to be a shortcut or a tunnel through the very fabric of spacetime. Picture the universe as a vast piece of paper with two distant points on either end. The normal route between them is a long line across the surface. A wormhole would be like folding that paper so the 2 points touch and poking a pencil through the fold, creating a tunnel that dramatically shortens the journey. In theory, this could allow for instantaneous travel across unimaginable cosmic distances or even into the past or future. The basis for this idea, once again, comes straight from Einstein's equations of general relativity. Certain solutions describe these bridges connecting two separate points in spacetime, and they are just as mathematically valid as the equations that describe black holes. The allure of wormholes is undeniable, fueling countless science fiction stories with their potential for interstellar exploration and time travel. However, the practical challenges of creating or finding a stable, traversable wormhole are monumental, likely placing them forever beyond our reach. The first and greatest problem is that the kind of wormhole predicted by standard general relativity would be incredibly unstable. It would snap shut the instant anything tried to pass through it, effectively stranding or crushing any would-be traveler. To prop it open long enough to be useful, you would need a form of matter with negative energy density, often called exotic matter. This isn't just something we haven't found, it's something that defies classical physics. This exotic matter would have to exhibit negative gravity, creating a repulsive force to counter the wormhole's natural tendency to collapse. While quantum mechanics allows for tiny, fleeting regions of negative energy under specific conditions, the sheer amount needed to stabilize a wormhole large enough for a person, let alone a spaceship, is almost beyond comprehension. Furthermore, even if such a wormhole could be created and stabilized, it would present profound paradoxes, most famously the grandfather paradox of time travel. If you could travel back in time, you could potentially prevent your own existence, creating a logical inconsistency that physics generally abhors. Some theories suggest that quantum mechanics or some yet unknown law of causality would prevent such paradoxes from occurring, perhaps by making the wormhole collapse at the precise moment a paradox was about to happen. Despite these seemingly insurmountable hurdles, the study of wormholes is far from pointless. It serves as a critical stress test for our understanding of quantum gravity and the fundamental nature of spacetime, pushing the boundaries of general relativity and forcing us to ask deeper questions about what is truly possible in our universe. For now, they remain one of the most exciting and elegant ideas in theoretical physics, a beautiful reminder that the universe's rulebook might still have a few chapters we haven't yet learned to read. But what if the very act of observation, the foundation of all science, is itself an illusion? Our journey takes a deeply philosophical turn into one of the most unsettling ideas in all of cosmology, a thought experiment that challenges the very nature of existence and memory. This is the Boltzmann brain paradox, named for the 19th century physicist Ludwig Boltzmann, who helped pioneer the field of statistical mechanics. The paradox emerges from a seemingly straightforward question: why does our universe appear to have such a structured, low-entropy past? Entropy, a measure of disorder, always increases over time, as stated by the second law of thermodynamics. We see this everywhere. A hot cup of coffee cools down, a neat room becomes messy, a star burns out. The universe is constantly moving from a state of order to disorder. This leads to a profound puzzle. For entropy to be increasing now, it must have been even lower in the past. The early universe, at the moment of the Big Bang, was in a state of exquisitely low entropy, an incredibly ordered and unlikely configuration. This is the ultimate free lunch that physics has struggled to explain. Why did the universe start in such a special, low-entropy state? The Boltzmann brain offers a terrifying answer: maybe it didn't. The argument runs that in a sufficiently vast and ancient universe, or within an eternal multiverse, random quantum fluctuations will eventually conspire to create order out of chaos. Given enough time, the random jostling of particles will, by sheer chance, assemble a fully formed, self-aware brain, complete with false memories of a past that never actually happened. This brain would suddenly pop into existence, floating in the void, believing itself to be a person with a lifetime of experiences, only to almost instantly disintegrate back into disorder. The true horror of this idea becomes clear when you apply it to yourself. How can you be certain that you are not a Boltzmann brain? Your memories of reading this script, your knowledge of the world, your sense of a continuous life, all of it could be a random, momentary fluctuation in the cosmic foam. The universe you think you observe, with its galaxies and history, might be nothing more than an elaborate hallucination packaged inside a spontaneously generated consciousness. This isn't just a quirky philosophical puzzle, it's a direct assault on the reliability of empirical evidence. If Boltzmann brains are not just possible but statistically more likely than entire evolved universes, then science itself is built on a foundation of sand, as any data we collect could be a fiction. Unsurprisingly, cosmologists have devoted significant effort to resolving this paradox, as it essentially invalidates their entire field of study. The most common rebuttal is that a universe that produces Boltzmann brains is not a universe we should expect to find ourselves in. The overwhelming majority of these disembodied minds would experience pure, random chaos or nonsensical sensory input. The odds of one fluctuating into existence with a perfectly consistent and ordered set of memories, exactly like yours, are astronomically smaller than the odds of our universe having a genuine low entropy beginning. Therefore, the fact that we perceive a coherent, lawful reality is powerful evidence that we are not Boltzmann brains and that our past is real. This effectively uses our own ordered observations as proof against the hypothesis. Ultimately, the Boltzmann brain paradox is less about brains floating in space and more a sharp tool used to test our cosmological models. Any theory that predicts Boltzmann brains are common or inevitable, such as certain models of an eternal inflationary multiverse, is considered deeply flawed and in need of revision. The paradox forces physicists to favor models that have a well-defined beginning and a clear explanation for low initial entropy, pushing us toward theories like cosmic inflation. It serves as a cosmic reality check, a reminder that our theories must not only explain what we see, but must also ensure that we, the observers, are a likely product of the cosmos rather than a statistical ghost. It is a battle between probability and perception, and so far, our consistent reality is winning. Boltzmann presented a bold and elegant alternative to dark matter by modifying Newton's laws. Its initial formulation was incomplete, operating outside the framework of Einstein's general relativity. This limitation inspired physicists to develop more sophisticated theories that could incorporate MOND successes while playing by the rules of modern cosmology. The most ambitious of these is tensor vector scalar gravity, or TeVeS, developed by the renowned physicist Jacob Bekenstein. This theory represents a full-blown relativistic extension of MOND, an attempt to rebuild the foundations of gravity itself to do away with the need for invisible particles. TeVeS doesn't just add a simple adjustment, it introduces new fields that interact with the fabric of spacetime, altering how gravity behaves in specific regimes. At its heart, TeVeS proposes that gravity is not solely mediated by the curvature of spacetime, as described by Einstein's tensor field. Instead, it introduces two additional players, a vector field and a scalar field. Think of it like this: if standard gravity is a solo musician, TeVeS is a trio. The tensor field remains, representing the standard geometry of general relativity. The new scalar field is a function that takes on a single value at every point in space, and it is primarily responsible for producing the MOND-like behavior that flattens galaxy rotation curves. The vector field, which has both a magnitude and a direction, ensures the theory remains consistent with special relativity and other well-tested principles. The intricate interplay between these three fields is designed to kick in only when the acceleration due to gravity becomes incredibly weak, perfectly matching the conditions at the outer edges of galaxies where dark matter's influence was first inferred. This complex machinery allows TeVeS to replicate MOND's stunning successes at the galactic level. For many individual spiral and dwarf galaxies, The theory can accurately predict the rotation speeds of stars and gas without invoking a single particle of dark matter. The gravitational boost provided by the scalar field acts as a substitute for the missing mass, holding these fast-moving stars in their orbits. For proponents, this is the theory's greatest strength. It explains the observations using only the matter we can directly see and detect, adhering to a principle of parsimony often valued in science. It offers a universe that is, in a sense, more straightforward and less mysterious, where the laws of physics are simply different than we assumed rather than requiring us to find an entire new form of matter that has eluded detection for decades. However, the path for TeVeS has been fraught with severe challenges, particularly when its predictions are applied to the largest cosmic scales. The theory struggles mightily to explain the observed gravitational lensing around massive galaxy clusters. When light from distant galaxies bends around a foreground cluster, the amount of bending reveals the total mass present, both visible and invisible. In numerous instances, like the famous bullet cluster, the lensing measurements show a gravitational field that is completely separated from the visible matter. Dark matter theory handles this elegantly, explaining it as a cloud of collisionless WIMP that passed through the galactic collision. TeVeS, which ties gravity directly to the distribution of visible mass, finds it extremely difficult to reproduce this specific result without resorting to some contrived adjustments, undermining its initial simplicity. Furthermore, TeVeS has faced significant hurdles in replicating the precise features of the cosmic microwave background, the fossilized light from the early universe. The patterns of hot and cold spots in this radiation are a sensitive recorder of the universe's composition and evolution. The standard lambda CDM model, which includes dark matter and dark energy, matches this data with phenomenal accuracy. To even come close, TeVeS requires introducing additional, exotic fields or parameters that begin to make the theory look as complex and arbitrary as the dark matter it seeks to replace. It also has difficulty naturally explaining the observed large-scale structure of the universe, the vast cosmic web of filaments and voids that formed over billions of years. The gravitational scaffolding provided by dark matter is a key ingredient in this formation process, and without it, TeVeS must work much harder to explain how such structure emerged in the time available. These cumulative challenges are the primary reason TeVeS and its relatives have not gained widespread acceptance within the mainstream cosmological community. While admired for their ingenuity and for forcing a rigorous re-examination of our assumptions, they are largely seen as elegant solutions to a specific set of problems that create even larger problems elsewhere. The constant need for adjustment to fit new data stands in stark contrast to the dark matter paradigm, which successfully explains a breathtakingly wide range of phenomena, from galaxy rotations to cluster collisions to the CMB to the large-scale structure, with a single, coherent postulate. The failure to provide a more compelling alternative has, for now, solidified dark matter's position as the leading explanation, a testament to the fact that in science, the theory that explains the most with the least amount of special pleading usually wins the day. Yet for all its peaceful patience, the zoo hypothesis presents a very specific vision of cosmic ethics. But what if the truth is far more grim? What if the reason for the great silence isn't a benevolent prime directive, but a universe-wide state of paranoid terror? This brings us to one of the most unsettling and persuasive answers to the Fermi paradox, the dark forest solution. This theory paints the cosmos not as a collaborative sanctuary, but as a deadly, silent hunting ground where every civilization is a hidden hunter, terrified of revealing its location. The dark forest metaphor was famously popularized by the science fiction author Liu Cixin in his renowned trilogy, but its roots are firmly planted in the cold, logical soil of game theory. Imagine a dark forest at night filled with hidden hunters. Each hunter knows there are others but cannot see them or know their intentions. The first thing you hear is a twig snap. What do? The most rational, survival-maximizing strategy is not to call out a friendly greeting. It is to immediately aim your weapon in the direction of the sound and fire. Because in this scenario, the cost of being wrong about a stranger's goodwill is instant annihilation. The only guarantee of safety is to strike first and eliminate any potential threat before it can do the same to you. Now, scale this logic up to a galactic civilization that has spent millennia evolving, a culture that has everything to lose. The ultimate rational choice is to remain absolutely silent, listen intently, and be prepared to obliterate anything that foolishly announces its presence. This terrifying logic is built upon a few brutal axioms about the nature of intelligent life. First, survival is the primary need of any civilization. Second, civilizations continuously expand and consume resources, but the universe's resources are finite. This sets up an inevitable competition for survival. And third, and most crucially, there is no way to know for certain the intentions of another civilization. The technological gap between two species could be thousands or millions of years. To a more advanced civilization, we might appear as little more than insects, either to be ignored, studied, or most likely, swiftly eradicated as a potential future nuisance. The sheer ease of launching a relativistic kill vehicle, a simple chunk of rock accelerated to a significant fraction of the speed of light, makes cosmic genocide tragically simple for any species that has mastered interstellar travel. Why risk a conversation when a preemptive strike is so cheap and guarantees your safety? This theory stands in stark, chilling contrast to the optimistic principles that have guided programs like SETI for decades. The SETI paradigm has largely operated on a foundation of hopeful cooperation, the idea that advanced civilizations would be enlightened, benevolent, and eager to share knowledge. We have actively broadcast our presence, most famously with the Arecibo message, and we continuously listen for similar broadcasts from others. The dark forest theory suggests that this is not a search for friends, but a potentially suicidal act of shouting into the jungle. From this perspective, the fact that SETI has found nothing is not a failure but the best possible news. It means we haven't yet attracted the attention of a hunter. It redefines the great silence not as emptiness, but as the quiet of a billion civilizations holding their breath, all listening and none daring to speak. The profound and sobering implication of the dark forest is that it may represent the universe's ultimate equilibrium state. Any civilization that is loud, expansionist, or overly confident eventually meets a swift and silent end, removed from the galactic equation by a more cautious neighbor. The only civilizations that survive to old age are the paranoid, the stealthy, and the secretive. They are the ones who have learned to hide their energy signatures, to cloak their worlds, and to move through the galaxy with extreme prejudice towards any potential competitor. This isn't a universe of a unified galactic federation. It's a universe of isolated, terrified survivors, where the first and only rule of first contact is to shoot first and ask questions never. In such a cosmos, our continued existence may depend entirely on our ability to learn the same grim lesson and fade as quietly as possible into the background static of the universe. But what if consciousness itself isn't just an emergent property of complex neural computation, but something far more fundamental, woven into the very fabric of the universe? This brings us to one of the most speculative and captivating ideas at the intersection of physics and philosophy, the theory of quantum consciousness. At its heart, this concept challenges the dominant materialistic view in neuroscience, which posits that consciousness is simply a byproduct of the brain's electrical and chemical activity, a sophisticated program running on the wetware of our neurons. Proponents of quantum consciousness propose something far more radical, that the enigmatic phenomenon of subjective experience cannot be explained by classical physics alone, and may require the strange, non-local, and probabilistic rules of the quantum world. The most famous and developed version of this theory is the Orchestrated Objective Reduction Model, or ORCH, put forward by renowned physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. Their collaboration is itself a fascinating bridge between two vastly different worlds of expertise. Penrose brought his deep mathematical insight, particularly from his work on quantum gravity and the nature of reality, while Hameroff provided the biological context, searching for a specific structure within the brain where such quantum effects could be physically possible. Their theory suggests that consciousness arises from quantum vibrations happening inside structures called microtubules, which are tiny protein skeletons found within the neurons of the brain. These microtubules are far more than simple scaffolding. The ORCH model proposes they are incredibly sophisticated quantum processors. The process begins with a quantum superposition within these microtubules. This is the bizarre quantum state where a particle exists in multiple potential states simultaneously. Penrose and Hameroff suggest that these superpositions can occur in the tubulin proteins that make up the microtubules. These quantum states can then become entangled across vast networks of neurons, creating a unified quantum field. But here's the crucial part. According to Penrose's earlier work on quantum gravity, such superpositions are inherently unstable. He theorized that gravity would eventually cause this quantum wave function to collapse after a certain period, a process he called objective reduction. This collapse from a cloud of probabilities into a single, definite state is not random, but is orchestrated by the biochemistry of the brain. It is in this moment of orchestrated collapse, this quantum transition, that Penrose and Hameroff propose a momentary flash of conscious experience occurs. The continuous stream of consciousness we experience would then be a rapid sequence of these quantum events, like frames in a movie. This theory makes several breathtaking implications. First, it positions consciousness not as a computation, but as a fundamental feature of the universe, intimately tied to the very physics that governs reality at the Planck scale. In this view, the brain isn't creating consciousness like a computer creates a software program. It is rather an exquisitely tuned receiver or amplifier for a proto-consciousness that is already inherent in the fabric of space-time. This perspective resonates with panpsychist philosophies, which suggest that some form of mind or experience is a universal property of all matter. Secondly, ORCH offers a potential explanation for the hard problem of consciousness, the question of why and how we have qualitative, subjective experiences at all. The non-algorithmic, non-computable nature of the wave function collapse could, in theory, account for the free will, intentionality, and unique qualia that define our inner lives, elements that many argue can never be explained by deterministic classical processes. However, this revolutionary theory has faced intense criticism and skepticism from the broader scientific community, particularly from neuroscientists and physicists. The primary objection is the issue of decoherence. The warm, wet, and chaotic environment of the brain is considered the absolute worst place for delicate quantum states to survive. Quantum superpositions are notoriously fragile and are easily destroyed by interactions with their surrounding environment, a process that happens almost instantly outside of ultra-cold, ultra-controlled laboratory conditions. Critics argue that any quantum coherence in microtubules would be obliterated in picoseconds, far too quickly to play any meaningful role in neural processes or conscious thought, which operate on a millisecond timescale. They maintain that classical physics is more than sufficient to explain the brain's functioning. Furthermore, many neuroscientists point out that there is no direct evidence linking microtubules to consciousness in the way the theory describes. While anesthetics, Hameroff's area of expertise, are known to act on microtubules, this correlation does not prove causation. The mainstream view remains that consciousness is most likely an emergent property of the complex network of neurons firing in patterns, and that invoking quantum mechanics is an unnecessary complication, a solution in search of a problem. Despite the criticisms, the theory of quantum consciousness continues to captivate the imagination because it represents a daring attempt to bridge two of the greatest unsolved mysteries in science: the nature of reality as described by quantum physics and the nature of our own inner reality. It pushes the boundaries of both fields, forcing a conversation between them and reminding us that the most profound answers may lie not in one discipline alone, but in the uncharted territory where they meet. But just as we grapple with the quantum mysteries of the mind, our cosmic journey compels us to look outward again, to an alternative vision of creation that completely reimagines the Big Bang. We've explored cosmic inflation as the leading theory for those first moments, but what if the trigger for our universe wasn't a rapid expansion of space, but a spectacular collision between entire worlds? This is the ekpyrotic universe model, a daring hypothesis born from the higher dimensional playground of string theory. The name itself comes from the Greek word for conflagration or fire, and it paints a picture of our cosmic origin not as a bang but as a tremendous clash. This model is built upon the same foundational idea as the cyclic universe, that our reality exists on a three-dimensional membrane or brain floating within a higher dimensional space. But unlike the cyclic model's endless series of collisions, the original ekpyrotic scenario envisioned a one-time event. In this view, our universe's brain was not alone. A second parallel brain coexisted in the void. These two brains, drawn together by a mysterious force, eventually moved on a collision course. The moment of impact, the violent meeting of these two colossal structures, released an unimaginable amount of energy. This energy flooded our brain, heating it to incredible temperatures and filling it with the radiation and matter that would eventually coalesce into everything we see today. In essence, the Big Bang was not the beginning of space and time, but a profound event within a pre-existing, higher dimensional reality. This collision does more than just create a hot, dense state. It also provides a compelling explanation for the key features of our universe, most notably the near-perfect uniformity we see in the cosmic microwave background. In the inflationary model, this uniformity is explained by the rapid stretching of a tiny, pre-equilibrated region. The ekpyrotic model offers a different pathway. As the two brains approach each other in the higher dimensional bulk, quantum fluctuations cause their surfaces to ripple slightly. During the collision, these tiny ripples in the brains are imprinted onto the newly created hot plasma as variations in density. These minute imperfections are the seeds from which all cosmic structure, galaxies, clusters, and the vast cosmic web will eventually grow. Because the brains were very nearly flat and parallel before they collided, the resulting universe inherits that flatness, elegantly explaining why the geometry of our cosmos is so perfectly balanced on the knife's edge between expansion and collapse. A crucial distinction separates this from the cyclic models we discussed earlier. While both involve brain collisions, their timelines and ultimate fates are profoundly different. The original ekpyrotic model typically describes a single, unique event, our universe's one and only birth from a collision. The cyclic model, by contrast, proposes an eternal, repeating loop where a collision is both the end of one cosmic epoch and the beginning of the next, driven by the evolving nature of dark energy. The ekpyrotic model is more focused on providing a specific, one-time alternative to inflation for the initial conditions of our universe without necessarily committing to an endless cycle of rebirth. Despite its elegance and theoretical appeal, the ekpyrotic universe remains a niche hypothesis, largely due to significant challenges. For one, crafting a realistic model that smoothly transitions from the moment of collision into the familiar, hot Big Bang universe has proven to be incredibly difficult mathematically. This is known as the graceful entrance problem. Furthermore, while it can produce a nearly scale invariant spectrum of density fluctuations similar to inflation, some detailed predictions about the gravitational waves generated in that primordial era differ. The search for these primordial gravitational waves is a key battleground for cosmological theories. Inflation generally predicts a strong signal, while the ekpyrotic scenario suggests it would be virtually undetectable. The fact that we have not yet found this signal keeps the ekpyrotic model alive as an intriguing, if minority, viewpoint in cosmology. It stands as a powerful reminder that even our most foundational stories about the universe's beginning are still open to radical and breathtaking reinterpretation. Imagine if the most elusive stuff in the universe wasn't made of some exotic, invisible particle, but of the most extreme objects we know of, black holes. This is the compelling premise behind the theory of primordial black holes. The standard story of black hole formation is a tale of stellar death, where a massive star collapses in on itself at the end of its life. But this theory proposes a far more ancient origin story. It suggests that in the first frantic second after the Big Bang, the universe was a seething, dense soup of energy. Within that chaos, extreme fluctuations in density could have caused some regions to become so unimaginably dense that they collapsed directly into black holes without ever needing a star to seed them. These would be true cosmic fossils, relics from the universe's very first moments, and according to this idea, they could account for the entire 27% of the cosmos we call dark matter. The possible sizes of these ancient objects are a key part of their mystery. Unlike their stellar mass cousins, which are typically between 5 and 100 times the mass of our Sun, primordial black holes could theoretically exist across a vast spectrum. They could be as small as an asteroid, with the mass of a mountain compressed into a space narrower than an atom, or they could be true behemoths, thousands of times more massive than the Sun. This range makes them incredibly versatile candidates. For instance, if most primordial black holes were around the mass of a large asteroid, there would need to be a staggering number of them. Trillions could be drifting through our solar system right now, utterly undetectable by the light they emit. On the other hand, if they were mostly of intermediate size, say between 10 and 1,000 solar masses, their numbers would be fewer, but their gravitational influence would be just as significant in shaping the cosmos. One of the most compelling pieces of evidence for this theory comes from the phenomenon of gravitational microlensing. When a massive object passes between us and a distant star, its gravity acts like a lens, bending the starlight and causing the star to temporarily appear brighter. Telescopes have been monitoring hundreds of millions of stars for decades, searching for these characteristic brightening events. They have found them, and some of these events are incredibly brief and caused by objects that are completely dark. While many of these are likely just faint, ordinary stars, a population of isolated, planet-sized primordial black holes would produce an identical microlensing signature. The data isn't conclusive yet, but it leaves the door wide open for these ancient objects to be out there, their presence revealed only by the way they warp the fabric of space-time around them. The story took an even more intriguing turn with the first detections of gravitational waves by LIGO and Virgo. These observatories recorded the ripples in space-time caused by the mergers of black holes. Surprisingly, some of these black holes were in the so-called mass gap, heavier than what should be possible from a typical stellar collapse, yet lighter than the supermassive monsters at the centers of galaxies. This is precisely the mass range where primordial black holes could be abundant. The fact that we are detecting pairs of these objects merging raises a fascinating possibility. If they were formed in the early universe, they wouldn't be isolated, they'd be born in clusters. This means pairs of them could have been orbiting each other for billions of years, slowly spiraling inward until they finally collide in a catastrophic event that we can now observe from over 1 billion light-years away. Of course, this tantalizing theory faces significant hurdles. If there were a vast population of small, asteroid-mass primordial black holes, they would occasionally collide with objects like neutron stars. Such a collision would deposit a tremendous amount of energy, potentially destroying the neutron star in a way that would be visible as a bright explosion. The fact that we don't see a high rate of these events places strict limits on how many small primordial black holes can exist. Similarly, if they were too numerous, their collective gravity would disrupt the delicate structure of tightly bound star clusters, an effect that also isn't widely observed. These constraints have largely ruled out the idea that primordial black holes make up all of the dark matter, but they leave plenty of room for a scenario where they are a major component, perhaps working in concert with another form of dark matter like WIMP. The search for these ghostly remnants is a multi-pronged effort that leverages the full power of modern astronomy. Projects like the Subaru Hyper Subprime Cam Survey are scanning vast areas of the sky, meticulously cataloging microlensing events to build a statistical picture of the invisible masses drifting through the galactic halo. Meanwhile, the next generation of gravitational wave observatories, like the space-based LISA antenna, will be sensitive to mergers of much larger black holes, potentially revealing an entire population of primordial giants that have so far remained hidden. Finding conclusive proof would be a monumental discovery, instantly solving two cosmic mysteries at once. It would identify the nature of dark matter and provide a direct window into the physics of the universe's first second of existence, a time far earlier than any light we can currently see. Imagine for a moment that every version of string theory we've ever conceived, with its different dimensions and vibrating strings, isn't a separate idea at all, but just a single chapter in a much larger, more magnificent story. This is the breathtaking vision behind M-theory, a proposal that emerged from the work of physicist Edward Witten in the 1990s. Before M-theory, string theory was a family of 5 distinct models, each with its own mathematical rules, each claiming to describe the fundamental nature of reality. It was as if we had 5 different maps of the same unknown continent, all contradicting each other. Witten's stunning insight was that these weren't rival maps, they were just different projections of a single, deeper reality. He showed that all 5 string theories, along with a related idea called supergravity, are actually different faces of one underlying 11-dimensional framework. The M in M-theory is intentionally enigmatic. It can stand for membrane, master, magic, or even mystery, reflecting the fact that its full nature is still being unraveled. This unification is more than just a mathematical convenience. It's a monumental leap toward a truly complete theory of everything. By weaving together all the string theories, M-theory naturally incorporates gravity alongside the other fundamental forces from the very beginning. It achieves this by adding an 11th dimension, a conceptual shift that transforms the entire picture. In this expanded view, the fundamental objects are no longer just one-dimensional strings. They can also be two-dimensional membranes or branes, and even higher dimensional objects known as p-branes. These branes can exist in many dimensions, a 2-brane, a 3-brane, and so on. Our entire universe with its 3 spatial dimensions could be such a brane, a vast floating sheet embedded within a higher dimensional space. This elegantly explains why we perceive only 3 dimensions of space. The fundamental strings that make up our particles and forces are stuck to our particular 3-brane, like waves confined to the surface of the ocean, while gravity, described by a closed loop of string, can leak out into the full 11-dimensional bulk. The mathematical elegance of this framework is its most compelling feature. It provides a powerful toolbox that can seamlessly connect the 5 string theories through transformations called dualities. For instance, a duality known as T-duality shows that a string theory compactified on a large circle is physically equivalent to a different string theory compactified on a very small circle. Another, called S-duality, connects a theory with a strong force to a different theory where the force is weak, making previously intractable calculations suddenly solvable. These dualities are the mathematical magic tricks that reveal the profound unity beneath the surface, suggesting that M-theory isn't just a patchwork of ideas, but a coherent and self-consistent description of reality at its most fundamental level. Yet, for all its breathtaking beauty and promise, M-theory remains one of the most ambitious and frustratingly theoretical constructs in all of physics. Its primary challenge is that we still lack a complete formulation of it. We don't have a single defining equation that encapsulates the entire theory. It's like having a detailed blueprint for a revolutionary engine without knowing the exact fuel it needs to run. This incompleteness makes it incredibly difficult to extract testable predictions that could be verified in a laboratory or through astronomical observation. The energy scales required to probe the extra dimensions or the fundamental strings are so phenomenally high, trillions of times beyond the reach of our most powerful particle accelerators, that direct experimental proof seems, for now, almost unimaginable. This places M-theory in a peculiar position. It is a magnificent castle of mathematical logic built on a foundation that remains, for the time being, just beyond our physical grasp. It stands as the ultimate expression of theoretical physics, a compelling, elegant, and potentially correct vision of the cosmos that challenges us to find a way to finally see it for real. But what if the tendency toward life isn't just a fortunate accident, but a fundamental feature of the cosmos? This brings us to a theory that takes a beautiful idea from our own planet and expands it to a truly cosmic scale, an extension of the Gaia hypothesis. Originally proposed by scientist James Lovelock, the Gaia hypothesis suggests that our planet Earth functions not just as a rock with life on it, but as a single, self-regulating superorganism. The biosphere, atmosphere, oceans, and geology all interact in a complex dance to maintain conditions that are favorable for life itself. It's the idea that life doesn't just adapt to its environment, it actively shapes and maintains it. Now, imagine applying that same concept to the entire universe. This cosmic Gaia theory proposes that the universe might possess its own form of large-scale self-regulation, a tendency to foster and preserve complexity and consciousness over immense spans of space and time. This grand idea finds a natural partner in the anthropic principles we discussed earlier. The universe's laws appear finely tuned for life, but a cosmic Gaia offers a dynamic mechanism behind that tuning. Instead of a static, lucky set of constants, it suggests an ongoing process where the universe and the life within it are in a continuous feedback loop. In this view, conscious observers aren't just passive beneficiaries of a lucky cosmos. They might play an active role in its very structure and evolution. This doesn't necessarily imply a conscious universe in the way we understand it, but rather a universe with an inherent bias toward increasing complexity, organization, and perhaps even meaning, with life and consciousness as its most profound expressions. To make this vast concept relatable, we can look at beautiful analogies from our own world. Think about how a forest regulates its own temperature through transpiration, or how the salinity of the oceans is maintained within a narrow band that allows marine life to thrive. On a cosmic scale, one could speculate that the violent deaths of massive stars, the supernova that forge heavy elements like carbon and oxygen, are not just random explosions, but essential processes in a galactic-scale recycling program, distributing the very ingredients for planets and life across interstellar space. Even the mysterious force of dark energy, which is accelerating the expansion of the universe, could be seen in this light. While it seems to be driving galaxies apart, this expansion may also be creating the vast, quiet spaces necessary for complex structures to evolve without constant catastrophic interference, effectively allowing cosmic islands of life the peaceful solitude they need to grow. However, this breathtaking vision inevitably draws sharp criticism, primarily around the charge of teleology, the idea that the universe is directed toward a specific purpose or goal, like fostering life. Mainstream science largely rejects teleological explanations because they can veer into the realm of philosophy or religion rather than testable, predictive science. Critics argue that seeing a purpose in cosmic evolution is a classic example of anthropocentrism, of us projecting our own human desires for meaning onto the cold, impersonal machinery of physics. They contend that the apparent fine-tuning for life is a classic selection effect. We can only observe a universe that allowed for our existence, so it's no surprise we find ourselves in one that seems tailored for us. The challenge for a cosmic Gaia theory is to move beyond this appealing metaphor and propose concrete, falsifiable mechanisms for how this universal self-regulation could possibly work across billions of light years. Despite these valid criticisms, the idea remains a profoundly inspiring one. It represents a shift in perspective from a universe that is cold and indifferent to one that is potentially generative and fecund. It connects us to the cosmos not as accidental specks, but as active participants in a grand, unfolding process that has, over 14 billion years, transformed a featureless soup of energy into galaxies, stars, planets, and beings capable of wonder. Whether this is a physical reality or a powerful metaphor, it encourages a sense of cosmic responsibility and awe, a feeling that we are part of something vastly larger and more interconnected than we can fully comprehend. It's a theory that may forever straddle the line between science and philosophy, but it challenges us to think about the universe not just as a place that has life, but as a process that is alive in the most magnificent sense. Now, let's venture into one of the most radical and mind-warping ideas in all of cosmology, a theory that turns the cosmos inside out. This is black hole cosmology, the proposal that our entire universe, with all its hundreds of billions of galaxies, might actually exist within a black hole. In this astonishing view, every black hole in our universe could be the seed for an entirely new, separate universe, meaning we might be living inside a black hole that itself resides within a parent universe, part of an infinite chain of cosmic reproduction. The theory elegantly tackles one of physics' most vexing problems, the singularity. At the heart of a black hole, general relativity predicts a point of infinite density where the laws of physics break down. Most physicists see this as a sign that the theory is incomplete. Black hole cosmology offers a stunning way out. What if there is no true singularity? Instead, the incredible collapse of matter that forms a black hole doesn't stop at an infinitely small point, but rather rebounds in a massive, explosive bounce, a new Big Bang. From the perspective of someone inside the newly formed universe, this event looks like the beginning of everything, while from the outside, it just looks like a black hole. This transforms the terrifying singularity from a dead end into a doorway, a portal to an entirely new space-time. This concept also provides a potential explanation for the universe's ongoing expansion. The energy powering our universe's growth could simply be the residual momentum from that initial rebound, the cosmic echo of the gravitational collapse that created our parent black hole. Furthermore, the observed acceleration of that expansion, which we attribute to dark energy, might be linked to the properties of the singularity bounce mechanism or the interaction with the higher dimensional space outside our black hole universe. It's a framework that reinterprets our greatest mysteries as features of our unique cosmic location within a much larger multiverse. This idea finds a fascinating and more developed form in physicist Lee Smollen's theory of cosmological natural selection. Smollen took the core idea and added a truly evolutionary twist. He proposed that the physical constants of a universe are not random, but are determined by the specific conditions of the black hole collapse that gave it birth. Furthermore, these constants would be slightly mutated or tweaked from those in the parent universe. This sets up a cosmic form of Darwinian evolution. Universes that produce more black holes are effectively more fertile. As each black hole creates a new universe, these daughter universes will inherit their parents' laws of physics, which were successful at making black holes. Over countless generations, this process would naturally select for universes with physical constants fine-tuned to maximize black hole production. This offers a compelling, non-theological explanation for the apparent fine-tuning of our universe. We live in a universe good at making black holes because that's precisely what it was selected for. Despite its breathtaking elegance and its clever solutions to major problems, black hole cosmology remains a fringe idea in mainstream physics. The primary criticism is a profound one. The theory is currently virtually untestable and unfalsifiable. We have no known way to peer outside our own universe to confirm the existence of a parent cosmos or to measure the properties of the higher dimensional space our black hole might be embedded in. Any predictions it makes about our universe are often identical to those of standard cosmology, making it difficult to design an experiment that could distinguish between the two. Without a clear path to verification, it remains in the realm of fascinating speculative metaphysics rather than established scientific theory. Yet it endures as a powerful testament to human imagination, a brilliant piece of cosmic poetry that challenges us to think about origins, endings, and our place in the cosmos in a completely new light. But within the bizarre rules of quantum mechanics, a new state of matter emerges that seems to rewrite this fundamental script, the time crystal. Imagine a clock that ticks forever without any energy input, or a wind-up toy that never winds down. That's the mesmerizing promise of a time crystal. First proposed by Nobel laureate Frank Wilczek in 2012, a time crystal is a structure that breaks time translation symmetry. This complex phrase simply means it has a rhythm, a repeating pattern in its state that persists over time, even in its absolute lowest energy state, known as the ground state. While all other matter settles into a quiet, motionless equilibrium when cooled to its ground state, a time crystal would continue its perpetual oscillation. It's not a machine that creates energy. That would violate the laws of thermodynamics, but rather a system that exhibits motion without ever dissipating energy. It's the closest thing to perpetual motion the universe might actually allow. The experimental race to create such an object was fierce, and the first successful demonstrations came just a few years after Wilczek's proposal. Scientists didn't find time crystals lying around in nature. They had to engineer them under incredibly controlled conditions. The key was to use a quantum system that could be kicked or perturbed in a periodic way. Researchers used chains of ions or dense clouds of atoms within diamonds, manipulating them with precise laser pulses. They would hit the system with a laser, then hit it again, establishing a driving rhythm. The astonishing result was that the system would respond not at the same frequency as the laser, but at a fraction of it. It was as if you tapped a bell every second, but the bell only chimed once every 2 seconds, establishing its own, slower, and perfectly stable rhythm that continued indefinitely as long as the driving force was applied. This broken symmetry, where the system's period is longer than the driver's period, is the hallmark of a discrete time crystal. This isn't just a laboratory curiosity. It points toward revolutionary applications, particularly in the field of quantum computing. The biggest hurdle for quantum computers is decoherence, the tendency of fragile quantum bits or qubits to lose their information due to the slightest disturbance from the outside environment. A time crystal, with its inherent stability and resistance to change, could provide a profoundly robust platform for storing quantum information. Think of it as an unshakable foundation in a world of constant quantum noise. A qubit encoded in the persistent, rhythmic state of a time crystal could potentially maintain its coherence for vastly longer periods, making practical quantum computation a much more achievable goal. This intrinsic stability could be the key to building the error-resistant quantum memory that the entire field is desperately seeking. Beyond practical technology, the existence of time crystals forces us to confront deep questions about the nature of time itself. Physics has long struggled with the arrow of time, why time seems to move only forward from the past to the future. Time crystals introduce a new kind of temporal order, one that is periodic and stable without a preferred direction. They represent a new phase of matter, much like solid, liquid, and gas are phases, but for time. Just as a material transitions from a symmetric liquid to an ordered crystal when cooled, a time crystal is a transition into an ordered state in the dimension of time. Studying these structures could open a window into physics beyond our current standard model, potentially revealing how complex phenomena like consciousness or cosmic evolution are intertwined with the fundamental fabric of time. The time crystal isn't just a new object, it's a new lens through which to view the universe's most persistent mystery. But if the bizarre world of quantum mechanics feels completely disconnected from the solid reality we experience every day, then our next theory offers a powerful and elegant bridge. This is quantum Darwinism, a fascinating framework that proposes a process strikingly similar to natural selection governs which quantum possibilities become our classical reality. At the heart of every quantum mystery, from Schrödinger's cat to the double-slit experiment, lies the measurement problem. How does the fuzzy, probabilistic world of quantum superposition collapse into the single, definite state we actually observe? Quantum Darwinism, championed by theorists like Wojciech, suggests the answer isn't found in a conscious observer, but in the environment itself. To understand this, we need to revisit the concept of quantum decoherence. When a quantum system like an atom in a superposition of two states interacts with its environment, it doesn't happen in isolation. That environment is made of countless particles, photons of light, air molecules, even the cosmic microwave background radiation. The quantum system becomes entangled with all these environmental particles, and this entanglement spreads the information about the system's state out into the world at the speed of light. This process, decoherence, is what rapidly destroys delicate quantum superpositions, making them appear to collapse into a classical state. But decoherence alone doesn't explain why we all agree on what that state is. Why does everyone measure the same position for the moon? This is where the Darwinian part of the theory comes in. Quantum Darwinism proposes that not all quantum states are created equal when it comes to survival in the environment. Some states are far more robust and durable when copied out into the surrounding world. These are called pointer states, and they are the ones that can withstand the constant buffeting from environmental interactions without being drastically altered. Think of it like a message being passed through a noisy crowd. A simple, clear message like "the cat is alive" might be accurately repeated by thousands of people even as it spreads. A more complex, fragile message like "the cat is both alive and dead" would be immediately corrupted and lost in the noise as the first person tries to whisper it to the next. The environment acts as a selective amplifier for pointer states. This is where the analogy to natural selection becomes so compelling. In biology, the environment selects for traits that increase an organism's fitness, allowing it to reproduce and pass on its genes. In quantum Darwinism, the environment selects for quantum states that are the most stable and that can be copied and proliferated most effectively. The pointer states are the fittest, and they are the ones that survive the process of decoherence to become objective facts. The countless photons and particles that have interacted with an object carry multiple, redundant copies of its pointer state information. This is why you and I can both look at a table and agree on its position. We are not directly sampling the quantum object itself. We are simply accessing the abundant classical information about it that has been broadcast into the environment. This framework elegantly solves the measurement problem without requiring any special role for consciousness or any mysterious collapse mechanism. The emergence of a classical reality is not a sudden event but a process of information proliferation. What we perceive as a collapse is simply our access to a consensus reality that has been forged through countless interactions between a quantum system and its environment. The theory has gained significant traction because it is grounded in the well-understood physics of decoherence and provides testable predictions. Experiments have begun to confirm that information about a quantum system is indeed copied into the environment in the redundant way the theory describes, offering a glimpse into the mechanism that transforms quantum possibility into shared classical experience. Yet after this breathtaking tour through 30 possibilities, from cosmic holograms to hidden dimensions, we must confront one final humbling theory. It's the simplest explanation of all, the null hypothesis for the great silence. We haven't found any signs of alien life because there is no one else out there to find. In a cosmos of 2 trillion galaxies, this seems almost incomprehensibly lonely, but it remains a stark possibility we cannot ignore. This idea doesn't require exotic physics or grand galactic conspiracies. It simply suggests that the chain of events leading from a sterile planet to a spacefaring civilization is so long and fraught with peril that most chains break, and ours might be the only one that didn't. This perspective finds its strongest voice in the rare Earth hypothesis, which argues that while simple microbial life might be common, the emergence of complex, intelligent, technological life requires such an improbable confluence of factors that Earth could be a cosmic aberration. It's not just about being in the habitable zone, it's about having a stabilizing large moon to prevent wild axial tilts, a magnetic field generated by an active core to shield the atmosphere from solar winds, the right amount of water and landmass, a Jupiter-like outer planet to deflect cometary bombardment, and a placid galactic neighborhood away from frequent sterilizing supernova. This theory posits that our planet isn't just a pleasant garden, it's a winner of a cosmic lottery that had to hit a dizzying number of jackpots in a row. The greatest filter in this scenario may be the very first step, abiogenesis, the spontaneous emergence of life from non-living chemistry. We've found the building blocks, amino acids and nucleobases on asteroids and in nebulae, suggesting the ingredients are universal. But going from that organic soup to a self-replicating system capable of evolution is a leap of staggering complexity. It might be that this event is not a near-inevitable outcome on a wet, rocky world, but a flash of such profound statistical improbability that it has only happened once in the observable universe. The fact that life on Earth appears to have begun almost the instant our planet cooled enough to support it could be misleading. We might not be an example of a common process, but the single, miraculous outlier. This view creates a profound tension with the foundational optimism of SETI, which has long operated on principles like the Drake equation. That equation is a wonderful tool for conceptualizing the possibilities, but it's built on a series of best guesses and hopeful estimates for each factor. The null hypothesis challenges every one of those estimates, suggesting that the values for the fraction of planets that develop life, the fraction where life becomes intelligent, and the longevity of civilizations might all be catastrophically close to zero. It reframes the silence of the cosmos not as a puzzle to be solved, but as the expected background state of a universe that is largely, perhaps entirely, barren of conscious thought. Ultimately, this isn't a pessimistic conclusion, but a deeply awe-inspiring one. It forces us to confront the breathtaking responsibility and fragility of our own existence. If we are alone, then the entire grandeur of the cosmos, the swirling nebulae, the exploding stars, the silent dance of galaxies exists for no audience but us. We are not just inhabitants of a pale blue dot. We are the universe's only known way of understanding itself. Every piece of art, every symphony, every act of love and curiosity becomes infinitely more precious, not less. It means that the future of meaning, discovery, and life itself rests not with some advanced galactic federation, but entirely in our hands. The silence is not an answer. It is the most important question we will ever be asked, and the work of filling it with meaning is now our cosmic purpose. And so, our incredible journey through the cosmos comes to a close 30 breathtaking theories, each a key unlocking a different door to the universe's deepest secrets. We've wandered through the infinite bubbles of the multiverse, felt the ghostly pull of dark matter, and questioned if our reality is nothing more than an elaborate simulation running on some alien computer. We've stood at the edge of black holes, pondered the nature of consciousness itself, and even considered the haunting possibility that we might be utterly alone in a silent, sprawling cosmos. What a wild, mind-expanding ride it has been. What makes these ideas so powerful isn't just their ability to explain the unknown, it's how they reveal the sheer brilliance and audacity of the human spirit. Each theory, from cosmic inflation to the holographic principle, represents a monumental leap of imagination, a testament to our relentless drive to look into the darkness and ask, what's out there? They push the boundaries of not only science but of philosophy and wonder, blurring the lines between what we can prove and what we can dream. They remind us that the universe is far stranger, more complex, and more magnificent than we could have ever imagined, and that the quest for understanding is one of the most beautiful adventures we can undertake. This is where the conversation turns to you. Every one of these theories started as a spark in someone's mind, a what-if that refused to be ignored. Now we want to hear your spark. Which of these 30 ideas captured your imagination the most? Did the chilling logic of the dark forest theory resonate with you, or does the elegant beauty of string theory's vibrating strings still have your mind buzzing? Perhaps you're a fan of the cosmic patience suggested by the zoo hypothesis, or maybe you think the rare Earth hypothesis is the most compelling answer of all. Share your favorite theory down in the comments and let's keep this incredible discussion going. We read every single one. If this journey through the edges of knowledge left you hungry for more, you're in the right place. Make sure to subscribe and hit that notification bell so you never miss our next deep dive into the enigmas of the universe. We're always exploring new mysteries, from the quantum weirdness of time crystals to the latest revelations from the James Webb Space Telescope. There's so much more wonder to uncover together. So as we sign off, we leave you with this final thought. However you see the cosmos, as a multiverse, a simulation, or a lonely island of life, never stop looking up. Never stop asking those big, beautiful questions. That sense of wonder you feel when you gaze at the stars is the very engine of discovery, the same curiosity that has propelled humanity from ancient stargazers to modern cosmic explorers. Keep wondering, keep searching, and never lose that awe for the magnificent, mysterious universe we call home.